ELF is the binary file format used on Linux and a few other operating systems. Other binary file formats include COFF, the Common Object File Format, and PE, the Portable Executable Format found on Windows, which is an extension of COFF. There's also Mach-O, which is used for Mac OS. But we're concerned with ELF. readelf is a utility for examining ELF files, just as you might guess. We can use readelf to see what's in our files, if they're ELF files. Hello.o is a 64-bit ELF file for x86-64. And hello is a 64-bit ELF executable for x86-64. Both hello and hello.o are 64-bit ELF files, but only hello is executable. We can list the sections in a file with readelf-s. Note the capital S. This looks jumbled because it is. Rows of the table are wrapped. For example, this is the header row, this is the first row, etc. If we add the -w flag for wide, we can see the table a bit better. The first section listed is a null section, right here. Often in ELF files, tables start with a leading null entry, and this is no exception. We'll see that again as we go on through. We see our Fred section. It's listed as type progbits, meaning it contains parts of the program binary, and it has flags A and X. If we look down at the bottom, we can see A is for allocate, meaning we should allocate space for it, and X is for execute, meaning we should mark its memory as executable. We also see .data. We also see it's marked as progbits, and it's got an allocate flag but no execute flag. But we also notice it's writable. If we didn't want that, we could solve that in two different ways. First, we could say, make it not writable. That would work, and it would be fine. A second way to solve it is to use a different section name. .rodata is a section name for read-only data. So let's try that. Let's be sure it still works. And now let's take a look at the section table. And we'll notice the W flag is gone. We also see the Note GNU Stack section. Notice that its size is 0. In fact, it begins at offset 290, and the very next section also begins at offset 290 because there's nothing in the Note GNU Stack section. This is not the stack. It's just a marker that will be consumed by the linker and will inform how the linker will declare the stack. Notice that the addresses are all zeros. Assigning addresses is usually the job of the linker or the program loader, so they're unspecified here. We can also see the offset into the file where each section starts and the size of the section. And these are both given in hexadecimal. Hexadecimal? Well, here's a little trick. Inside these parentheses, you can have math. And you can even do some bitwise operations. You can also use hex. A more general approach to converting hex to decimal and decimal to hex is to use Python. We can go the other way. We can take a look at the contents of our files by using a tool like XXD. Now on my system, I can install that with sudo apt install XXD. We can give this tool the file, an offset into the file, and a number of bytes. And we can use decimal or hexadecimal for the offset and length. The tool will then display the selected bytes as hexadecimal, along with a display of any single byte characters in the printable range, that is ASCII characters. So we can talk about it or we can do it. Let's go ahead and look at the RO data section in our file. So here's RO data, and we see that it's an offset hex 270 and size hex 16. So we'll say seek to 0x270, and the length is 0x16, and we'll give it the file. And there's the contents. We know what should be there, right? It should be the string hello assembly world followed by a new line, and that's in fact what it is. Notice this last period here is just indicating that this is not a printable ASCII character. It's in fact a control code. It's a new line. It's hex 0A or decimal 10. Notice that the output is printed with bytes in groups of 2. If that disconcerts you, you can say -G1 to change it to groups of 1. Same information, just a slightly different display. readelf has the ability to display the contents of a section 2. We can use -X to get a hex dump for all the sections with a given name. So let's try that for RO data. And again, you can verify this is the same information, right? There's 4865, there's 4865, and there's 4865. This is just printing in blocks of 4. The readelf approach is simple. Just give it the section name. But XXD is more flexible, and it can also reverse hex dumps back into binary files, and you should take some time to get familiar with both tools. ELF files have both sections and segments. Now remember, sections are programmer-controlled divisions of a program. Segments are regions of memory with the same access rules. The linker lays out sections into segments, and that can be controlled with a linker script, but that's beyond the scope of this class. Segments aren't named in ELF files, but referenced by index, and we can see them with -L. So let's try that. Well, this file hadn't been linked yet, so there are no segments defined. Let's try this with the fully linked file, hello. There we go. We see 4 segments. We see 4 segments. And we're going to ignore the first one for right now. The second segment is readable and executable. You can see that from the flags here at the end. And the fact that it's executable might lead us to believe this is going to contain our text section, which we named Fred. And in fact, if we look down here at the section to segment mapping, yes, that is in fact what's in that segment. A segment can contain more than one section. It can contain 0 sections, 1 section, 10 sections. In this case, it just contains 1. The next one, right, the third section, or section index 2, is readable but not executable or writable. And so we might conclude that's probably our read-only data, and sure enough, the segment mapping shows us that we're correct. Finally, we have a stack segment that is readable and writable, but not executable, just as we wanted. Now, this is also not the stack. This tells the kernel or the loader to create a non-executable stack for the process. Now, note, we don't set the stack size here, which is why you'll see that the size is 0 for this. There's nothing that gets loaded into memory. There's no address for it. It's just, again, a marker. The stack size is actually controlled by the kernel, and there's a tool to set that called ulimit. And the stack option is -s. You can read about that if you're curious. By default, it's about 8 megabytes for the main process thread. You should try commenting out the .note GNU stack section directive and redo this to see how it changes things. You might be surprised by the result. Let's go back to our section listing. Now, there are 3 sections here we haven't discussed: SymTab, StirTab, and SHStirTab. Now, they don't have an A flag over here. I mean, they don't get allocated, so they're not going to end up in memory. And they don't have an address assigned. Well, we can still use readelf to examine the content of these sections. Notice the type. SymTab is a symbol table, StirTab is a string table, and SHStirTab is also a string table. Let's start with the section header string table .shstirtab. The table begins with a null. I keep telling you that's just how ELF files work. So it begins with a null. This 2E is a period. 7.3 is S. 7.9 is Y, M, T, A, B, and then a terminating null. So it's .symtab. We see that after this we have a series of null terminated strings, and those null terminated strings are, in fact, the section names. There's .symtab, there's .stirtab, SHStirtab, Fred, and .rodata. The little periods in between them and at the end here are the non-printable nulls. We can also use -p. We can use that with a string table to see the strings. And there they are. And notice the numbers. The numbers are the hex offset to each one. So for example, we would see .stirtab at offset 9, but let's test that. This is offset 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Sure enough, right here we see, and there's a terminating null, .stirtab. So sure, that makes sense. If we looked at the raw section table, we wouldn't find any names in there at all. We'd find an index to each string listed. We'll take a look at that in a bit. So let's go ahead and look at StirTab. Now we see the name of the original file, hello.asm, and we see some other strings. But notice we see message and message_len, which were private strings, but we don't see the one public string we declared, _start. What happened? Well, this is an example where the tool isn't quite telling us the complete truth. Let's look at it with XXD. We'll use readelf to get the offsets again. So we'll seek to 20D8, and the length will be 2F. We'll put it in groups of 1, and there we go. Now, this first looks just the same as what we saw up here, right? Hello ASM, message len, looking much the same, but look, right here is start, and it's null terminated. Let's use -O and look for the actual offsets. So another switch is -O, and whatever value you give it here is added to the offset shown at the start of each line. We like that to start at 0, so we'll just pick minus 0x20D8. And now this starts with 0. So we can figure out where start begins. This is hex 10, or 16, so 10, 11, 12. Well, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 1A, 1B, 1C. Right? That's an underscore STA. Right? That's this piece right here. So it begins at offset 1C, and it's null terminated. Remember that. We'll come back to that. Notice what's really happened. It's decided to share underscore start with underscore BSS start. Right? We already have the underscore start in here. We might as well just share that. That's called string pooling, and it's not that unusual. Let's go back and take a look at the symbol table. We'll use -S, lowercase s, to look at it. So here's the symbol table, .symtab, and we see that it contains 8 entries, and you'll notice in this telling of it, it does show underscore start at number 4. Now that we're looking more closely at the ELF file contents, let's take a minute to see where it's all documented. There are 2 key sources of documentation on the ELF file format. The first is the man page. In section 5, there you go. And this contains a lot of useful information about the ELF file format. The other source of information is the header file that defines ELF. The specific structures and byte lengths are found here, and the meaning of the contents of the structures is found over here on the man page. So the first thing we see in the header file is a collection of types. Each of these types is defined in terms of the standard C integers. So for example, we can see that ELF32 ½ and ELF64 ½ are both 16-bit unsigned integers. And we can see that ELF32 word and ELF64 word are both unsigned 32-bit integers. There are some divergences. ELF32 address and ELF64 address are different sizes, as you might guess, right? ELF32 address is 32 bits, ELF64 address is 64 bits. Searching for symbol table, we see the structure of the symbol table. An ELF64 word is 4 bytes. Each of these is 1 byte. An ELF64 section is 2. So 4, 5, 6, 7, 8. An address is 8 more, that's 16. An X word is 8 more for a total of 24. Each symbol table entry is 24 bytes in length. Another way to find this out is to list the sections and look at the int size column, which is ES in the wide format. So here's our symbol table again, and we come over here and we find out that ES is 18. So each entry is hex 18 bytes. That is 16 plus 8, which is 24. Knowing this, we can use XXD to dump the table with 24 bytes per line, so each line is a complete symbol table entry. We'll use -G1. C24 tells us we want 24 columns, or in this case 24 bytes per line. There's our start. There's our end. We're going to go ahead and subtract off the starting offset so that we can have zero-based results. And then there's our file. And here is the symbol table. From the header file, we know that the first 4 bytes are the index into the symbol table. Do we? We check over here. We find out that this is the first entry. ST name. It's an ELF64 word, so it's 4 bytes, and it's the symbol name symbol table index. So in this case, it points to index 0000. This is in Little Indian. So this is the high byte and the low byte. Let's go ahead and take a look at for entry 1, we see that it points to offset 0001, which is right here. And that points to the string hello ASM and its null terminator. Remember that we figured out that the one we wanted was at index 4. 0, 1, 2, 3, 4. So right here is underscore start, and it's at 001C. So here's 10, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 1A, 1B, 1C. So we begin right here with this underscore, and that sure enough is underscore start. Knowing how to map from high-level details to low-level implementation and back is really important for reverse engineering.